In this video, we're going to introduce three-dimensional coordinate systems. So, up until now, we've plotted things in 2 dimensions using rectangular coordinates or a Cartesian coordinate system. So we're going to extend this notion to plotting some points in space. So, when we're talking about plotting these points in space, we're going to need 3 axes, because we need a direction that kind of goes in and out of the screen, if you will, and then one that goes left and right, and one that goes up and down. So we need 3 different directions that we need to describe. So we'll use that with 3 axes. Now typically when we're drawing in 3 dimensions, we draw the part where we have each of the 3 respective axes as being positive. So we would also want to imagine that this axis here is going backwards into the screen, as well as coming out of the screen. We would imagine this one that's going to the right is also going backwards to the left, and the one that's going up also goes down. All right, so typically the one we call that comes out of the screen or coming at you will be the x-axis. The one that's going left or right will be the y-axis, and the one that's going up and down will be the z-axis. We should note that we could have also made the positive z-axis go down rather than up. We use what's referred to as the right-hand rule. So imagine if your fingers were going along the x-axis and you curled them, or sorry, I should say the positive x-axis, and you curl them towards the positive y-axis, your thumb would be pointing up, and that's giving us a positive direction for the z-axis. If you did a left-hand rule and tried to do the same thing, your thumb would be pointing down, and that would say that your z-axis positive would be down rather than up. But our convention is to do it in this fashion, using that right-hand rule idea. All right, much like when we have plotting in 2 dimensions, or doing a 2-dimensional coordinate system, a rectangular coordinate system, I should say, the origin is going to be our intersection point of the axes. So the point here, that's where the common intersection of the x, y, and z axes will be the origin. Notice that a pair of 2 axes determines a plane, and those are going to be what are referred to as the coordinate planes. So from a picture standpoint, again, the plane that's determined by the x and the y axes is your xy plane. Your plane determined by the x and the z axes is your xz plane, and the one determined by the y and the z axes are the yz plane. So you can actually think of this one here, your xy plane, as your normal xy plane. It's just at the kind of on the floor, if you will. Notice, much like what we have in 2 dimensions, when we had our 2 axes, x and y, we had quadrants. In 3 dimensions, these planes will divide space up into octants, so there's 8 of them. And the one we typically worry about when we're drawing is this one that's where all the coordinates are positive. Here, the x, the y, and the z axes are all positive. So this octant here, that's determined by those 3, will be what we refer to as the first octant. We don't usually number the other ones, but the one is where all the x, the y, and the z are all positive, we refer to as the first octant. We describe points in space, much like we describe points in a plane, using coordinates. In this case, we have x, y, and z coordinates, so we have ordered triples rather than ordered pairs. So here, if we wanted to plot the point A, B, C, the A is your x coordinate, the B is your y coordinate, the C is your z coordinate. So that would tell us that we would go out A units, or perhaps back if it were negative. We would go right B units, or left if it were negative. And we would go up C units. So one of the ways you can imagine where this point is by looking at the corner of a box, where the ABC is the opposite corner from the origin. So that would be where that would be plotted. So you're going to go out that many units, out A units, over B units, and up C units. But again, we can imagine that as being a corner of a box, if you will. So let's do this by example. Let's say we want to plot the point 3, -1, 2. So the 3 is our x coordinate, so we would go out 3 units. Now, again, we have to use kind of perspective ideas when we're drawing these things, right? We can't literally have the x coming directly out of the screen at us. It's going kind of off diagonally, if you will. So when we want to go to the left 1 unit, since we have a -1 for the y-coordinate, I really want to take 1 unit, right? The space of 1 unit here and go to the left. Notice that if you were to just going across your y-axis, your -1 would be about here, and that looks a little too far to the right. But again, the reason for that is because we're doing that perspective idea, right? We're going out 3, we need to go literally over 1. Okay, so it looks like it's farther over, but we're thinking about trying to draw 3 dimensions on a 2-dimensional screen. And then the last coordinate here is 2, so we go up 2, and again, notice it doesn't quite go all the way up to 2 here, but we do notice that this is that corner of that box idea here, right? Here's the point, here's the origin, they're opposite corners of a box, and we can imagine that 3-dimensional box being drawn in. One of the things that we'll be doing in this chapter is looking at sets of points that satisfy certain characteristics. So let's look at this example where it asks us to describe and sketch the set of points that satisfy either the following equations or inequality. So in this case, we have y equals 2. This should remind you of looking at like what we have in 2 dimensions, where if you have a y equals 2, that gives you a horizontal line, because it says that the y-coordinate has to be 2, but the x-coordinate could be absolutely anything. It doesn't have to be, there's no restrictions on what the x can be. So in 2 dimensions, you would have that horizontal line at the y equals 2. Now we're in 3 dimensions in this case, however, so not only can the x be anything, but also the z can be anything. So what we get instead of a horizontal line here is we actually get a plane. Okay, so this is what I was mentioning here. The y-coordinate has to be 2, but the x-coordinate and the z-coordinate, no restrictions at all. So we end up getting a plane that crosses the y-axis of the point 0, 2, 0, and is parallel to the xz plane. So looking at that picture here, here's what would cross the y-axis. We get something drawn in here that would be parallel to the xz plane. And here, here I'm trying to show that it's going back and forth forever, this direction, up and down forever. But the y-coordinate's always 2 no matter what. Let's look at the following inequality. The x squared plus z squared is less than or equal to 4. Now we notice that the y is missing, but let's just think about what this shape would be just in terms of the xz. Say we have an x-axis and a z-axis and not worrying about y to start with. Well, if we change that inequality to an equal sign, we get a circle. We recognize that as an equation of a circle. It would be centered at the origin and a radius of 2. So if we think about then the less than or equal to sign, that would be everything that's inside the circle, or what we refer to as a solid disk, in the xz plane. All right, so now let's consider what happens with the y. Well, y could be it's missing, right? So the y could be absolutely anything because it will satisfy that inequality. Whether or not that inequality is satisfied has absolutely nothing to do with that y. So the y can be anything. So now we can imagine this being extended infinitely along the y-axis, and so we end up getting a solid cylinder that looks like so. All right, so let's do some other things that go along with three-dimensional coordinate system. One of the things we might want to know is what's the distance between 2 points. All right, so if I want to try to figure out what the distance between the point A and the point B here are with these given coordinates, I've drawn in the lines here to start with. So notice that the first thing I noted, I drawn at this line here that's kind of the bottom of this box. This would be the hypotenuse of a right triangle with AC and CD being sides. And then I also have another right triangle here, and so this distance from A to B would be the hypotenuse of a right triangle with AD and DB being sides. So we're applying the Pythagorean theorem twice will give us what the distance between these 2 points is. All right, so notice first that the distance between A to C, well, A has the x-coordinate of x1, B has an x-coordinate of x2, and that's how far out we've come. So the distance from A to C would just be x2 minus x1. Do absolute values in case that the point really is behind rather than in front. Likewise, when we do the distance from C to D, we're going from a y1 coordinate to a y2 coordinate. Notice that the x and the z would stay the same. We didn't go out or back, we didn't go up or down. So that distance would be y2 minus y1. So when we look at the square of the distance between those 2 points, we would have the length, the sum of the squares of the legs of the right triangle. So you'd have x2 minus x1 squared, and then a y2 minus y1 squared added together gives you the length of the hypotenuse squared. Okay? All right, so now we know what the length of AD is. We can use that now to help us figure out what the length of AB is. So looking at the picture again, the distance from D to B will be z2 minus z1, again absolute value in case of the order, if the z2 is actually lower than the z1. So now, when we do our Pythagorean theorem, we already know what AD squared is. DB squared will be z2 minus z1 squared, and so that'll be what the square of the distance from A to B is. So we define the distance from A to B to be the square root of the sums of those squares. One of the things we can use the distance formula for is to give us the definition of a sphere. This is the three-dimensional analog to a definition of a circle. You take a fixed point and a fixed distance, and you look at the set of all points that are that distance away from the fixed point. So we refer to the ABC as the center, and the R, of course, is the radius. Now that we have a distance formula, we can get this what's referred to as the standard form of the equation of a sphere. This looks very much like our standard form of the equation of a circle. We just have an extra piece for the z. So we'll have x minus a quantity squared plus y minus b quantity squared plus z minus c quantity squared equals r squared. All right, so let's use this to answer a couple of questions about spheres. Let's say we want to figure out what the center and radius are of a sphere with that equation. Notice that this is going to be a sphere because our x squared, y squared, and z squared are all positive, all added together, and they all have the same coefficient. We'll talk about different graphs when we have different coefficients. So now when we go to put this in standard form, we need to do a process which is referred to as completing the square. So let's recall how we complete the square. So the first thing we'll do is we'll gather our x's together, gather our y's together, gather our z's together, and move the constant to the other side. Now I need to factor these pieces as perfect binomial squares so I can see this standard form of the equation of the sphere. So in order to make this a perfect binomial square here, we'll need to divide the coefficient by 2 and square it. So I'll need to have a plus 1 in here. Likewise, for the y's, we'll need to divide this coefficient by 2 and square it. So we'll get a plus 9. Here, divide 10 by 2 and square it, we get 25. Again, the reason why we're adding these numbers in here is so that we can get these to factor as perfect binomial squares. All right. Of course, if I add 1, add 9, and add 25 on the left-hand side, I better do the exact same thing on the right-hand side. All right, so the first thing factors is x plus 1 quantity squared. Second thing factors as y minus 3 quantity squared. Third one factors as z minus 5 quantity squared. And that equals 36. All right, so now we can read off the center and the radius of the sphere. The center will be, notice the standard form has x minus a, y minus b, z minus c. So this is x minus a minus 1, so the x-coordinate is -1, the y-coordinate is 3, and the z-coordinate is 5. The radius is the square root of the number on the right-hand side, so in this case the radius is 6.